Hello, my name is Noah Weiss, and for my Stanford CS-153 final project, I built Farm. In 2 months, I'm bringing Farm to Dongguan, China to automate a factory. Farm is an architecture surrounding action reasoning models that enables higher performance on routine tasks like factory work. It's built on megabyte-sized adapter files, just 1% the number of parameters as the models they're adapting, and improves mean joint error by up to 43% on episodes outside the training set. To collect data and test the models, I purchased a UFactory A50 and understand the environment through 2 Intel RealSense cameras on custom 3D printed mounts. I also built and have open sourced a Unity app that lets you control, trigger recordings, and see the status of the robot and cameras through pass-through on the Meta Quest 3. Farm's architecture is built on 3 layers. I start from Physical Intelligence's Pi.5 model and run a one-time full fine-tune on a diverse selection of episodes to adapt the model to the ARM. Before feeding the data into the training sets, I apply a series of 10 perturbations to each frame to improve the robustness of the model. The next layer is an additional fine-tuning using GSE, a method recently out of Tsinghua University which creates 2 kinds of internal experts at the same time. A generalist that learns what's common across every task, and specialists that get good at a narrow subset of motions. This process only tweaks about 2.5% of the parameters, making it highly efficient. The result is a model that's broadly competent while exercising high precision in factory-specific tasks. The third layer is what makes Farm especially valuable and deployable on a factory floor, where repeatability and accuracy are incredibly important. For any specific repeated job, I train a LoRa, a tiny add-on file that encodes one skill exceptionally well. It works by, instead of taking the entire B by B matrix we just tuned, creating 2 much smaller B by A and A by B matrices, in this case A is 16, multiplying them together to retrieve a B by B matrix, and simply adding those parameters to the full fine-tuned GSE model. It takes about 30 demonstrations to achieve the accuracy improvements shown here. Because the files are so small, they could be stored locally on the factory floor, and as you compile more skills over time, this system eliminates the need for multiple massive base models. Even within skills that are already included in the training data for the fully fine-tuned GSE model, this additional layer can sometimes offer double the accuracy on tasks. To make this system genuinely useful on the factory floor, I implemented a task system. Simply specify the task. In this case, all I said was place the items on the box. With just this simple prompt, the agentic system begins by capturing an image to understand the setup. It identifies and maps the position of each object it observes and searches through its abilities to find matching skills for them, and carefully decides the best order to pick up the objects. It then creates a plan with verification checks after each action to make sure it completed the task before moving on to the next. Farm saves the plan, so if you want to do repeated work on consistent setups, you don't need to run the inference each time. After getting the ARM, one of my first goals was to test the spatial reasoning capabilities of modern LLMs. So I gave it a Rubik's Cube and presented it with some preset functions like how to rotate the top face clockwise, orient the front face, and a set point where all the top edges were visible to the camera. From there, with just a harness to the LLM, it was able to come up with a methodology to scan each face, write a solver, and then map the output moves from the solver to movements it could actually do. Here's another project where I had it play chess. Specifically, I gave it functions to pick up pieces from each square, taught it how to eliminate pieces, and from there it connected 2 stockfish engines to play each other. These projects showed me that LLM planning was already good enough for fairly complex tasks, but the models still couldn't execute the moves themselves, which is what pushed me towards VLA models. That led me to the training process. I ran lots of models to find the best way to build this system, running multiple different parameter settings on full fine-tunes and different orderings of the fine-tuned GSE and LoRa. One key finding was that going from 2 experts to 64 on GSE doubled training time but gave no performance improvements despite the far larger capacity. This allowed me to optimize incredibly fast training runs that were just a couple hours. This entire project was motivated by a trip I recently took to factories in China. Much of the labor done there could and should be automated. These VLA models are incredible pieces of technology, but their applications in these lower volume, high labor factories is underutilized. That's why in July, with much more progress on Farm, I'm going back to China to automate line work at a toy factory. I believe VLAs are currently bottlenecked by 2 solvable issues. One is data, which being deployed in factories solves. The other is enough consistency to be applicably valuable, which I believe is solvable with more work on my architecture. To conclude, there's one specific technical area that I find interesting but was not able to finish in time for this presentation. I was able to do some testing but not garner conclusive results. I want to see whether within LoRa's there's specific embeddings that generalize to the task they're completing. For example, do all plush pick-and-place tasks share a similar structure? Or what about tasks involving opening boxes? If they do, you could build a new task by composing these shared structures instead of collecting data and training a new model from scratch each time. This would massively cut down the data burden and deployment time of new jobs.